Ah, welcome. Here we are. This is it. The last real lesson that we're going to learn together. I want to let you guys know that I understand that this is a lot, but I also want you to understand that when you really get this, when this starts to connect and click for you, this is going to be immensely powerful. And I want you to understand how the interconnectedness between everything that we have done in this unit. We haven't learned any energy. We did not learn any energy in class together. All the energy stuff you learned online. So if you feel like you actually were able to learn this and you feel like you have a decent grasp on it, I mean, I can't think of a more college prep thing than to be able to use resources and teach yourself and advocate for yourself and ask questions when you need to and just take advantage of the situation. The situation is not ideal. We could have done so many more things if we were in class, but at least I am confident that you have been given the basics for understanding energy and how it all relates. So today, now that we've examined potential and kinetic energy calculations, total energy calculations, transfer of energy and conservation of energy on a roller coaster, we have done a chart, kind of bringing back free fall and vertical throwing to this. Today, well, let's see what we got. And yes, things are still going to fall to the ground. Okay, let's break this down. I have things on the screen in front of you that, in theory, you should know already. You should know that the total energy at one point in time is going to equal the total energy at another point in time. This was the fundamental principle that allowed us to solve those roller coaster problems. Several people let me know that some of the roller coaster problems the other day didn't make a lot of sense logically based on the scale, the drawing, and well done, well done. I think I mentioned it in the other video that they wouldn't, but I'm glad that we have the wherewithal to recognize when patterns and stuff don't necessarily make sense, but neither here nor there. When we did the charts earlier this week, and we had 1 second, 2 second, those were all different points in time. But if we looked over on the chart, the total energy side, the total energy was always the same. So all I'm just saying is that the total energy at one point in time equals the total energy at another point in time. And we know that total energy is potential and kinetic energy. So we understand that we add the PE and KE at one point in time. That's going to be the same thing as adding the PE and KE at another point in time. They're always going to equal the same number, okay? And another way of saying that is that PE is mgh, KE is 1/2 mv squared, PE is mgh, KE is 1/2 mv squared. So another way of thinking about it is mgh plus 1/2 mv squared equals mgh plus 1/2 mv squared. However, there's a curious thing about this. I can actually simplify that. There is a term, because it's in every single term here, there is a variable that can be canceled out. If I divide the whole thing by m, and I cancel all the m's out, what am I left with? I'm left with gh1 plus 1/2 v1 squared equals gh2 plus 1/2 v2 squared. Now, Vizito, where did these 1s and 2s come from? The 1s and 2s just correspond to a point in time. You can think about it as the first point in time, the second point in time. So the first height and the first velocity, the second height and the second velocity. They are not set in stone. So it's not like one point in time always is going to be v1. It's just one point in time and another point in time. So it could be any set points of time. It doesn't just have to be a very specific one. It doesn't have to be the very first point in time. It doesn't have to be the very last point in time. It just means one point in time and another point in time. Because we know it doesn't matter which two we select. When we add them up, the total energy never changes. Going back up here, the total energy at one point in time equals the total energy at another point in time. So if we know certain paired variables, we can actually use this equation. So let's see how this is going to work. Let's look at this problem in two separate ways. First, we're going to use it the way that we've been doing, using the mass. It says a 12-kilogram rock was falling off of a cliff. At one point in time, it was moving 8 meters per second while it was 42 meters high. How fast was it going when it was 12 meters high? This means I'm going to go ahead and solve for the PE and KE at one point in time, and I know that's got to equal the PE and the KE at another point in time. Now, we may have never exactly solved for a problem like this before, but when we did those roller coaster problems, this is essentially what we were doing. We know the PE is mass, gravity, height is 42. This is just, so we're going to use the 8 and the 42. They're paired together, so that's going to be 1 point in time plus 1/2, 12, 8 squared. So, okay, the 42 and the 8 are talking about the same point in time, so they have to be on the same side of the equation. And that's going to equal the PE and the KE at a different point in time, okay? So now we're looking at, I want to know how fast. I'm looking for the velocity that's paired with 12 meters high. So I'm going to do mass, gravity, and now the height we're going to use is 12 plus 1/2, 12 v squared, okay? So again, what's happening is we have two PEs and KEs, 42 and 8 are paired together, 12 and the velocity that we're looking for are paired together. That's why they're on the same side of the equation. Now, all we do is math. 12 times 9.8 times 42 plus 1/2 times 12 times 8 squared. When I do all of that, add it up, simplicity, 5,323.2 equals 12 times 9.8 times 12, 1,411.2 plus 6v squared. I'm going to minus the 1,411.2 from both sides, so I have 3,912 equals 6v squared. Divide both sides by 6. I get 652 equals v squared. And when I square root that jump, I get 25.53 meters per second. Now let's think about it. Does that make logical sense? Well, the height went from 42 to 12, so the height decreased. So we expect that the velocity will increase. This actually does kind of make sense. Now, let's think about it in another way. Let's try the new equation. Sorry about that. Let's try the new equation. I'm just going to erase some of this work so we can have some space. We saw it already. I'm going to leave some of the work. Okay, I'm just going to leave that on the side there. And I'm going to get a new color just so it looks nice and neat. All right, so the black marker was one way. The blue marker is going to be the other way. GH1 plus 1/2 V1 squared equals GH2 plus 1/2 v2 squared. So the question is, did we use the mass in the first time? We're not going to use the mass the second time. In theory, we should get the same answer. So let's see if we do. Gravity is 9.8. The first height is 42. Plus 1/2. What's the velocity that's paired with 42? 8. 1/2. 8 squared. Put that in parentheses. Equals 9.8. What's the second height? The second height is 12. What's the second velocity? I don't know. 1/2. That's going to be our variable. v2 squared. Okay. Math time. 9.8 times 42 plus 0.5 times 8 squared. So I'm getting 443.6 equals 9.8 times 12 is 117.6 plus 1/2 v squared. I'm going to minus 117 from both sides. And I get 326 equals 1/2 v squared. Divide both sides by 1/2. So I get 652 equals v squared. Oh. That looks familiar. So when I square root that, I get a velocity of 25.53. It is exactly the same. There is no difference. The mass cancels out, so you don't really even need it anymore. It just cancels out. So here's the situation. A brick falls from rest as shown in the picture in the left. At one point in time, it is moving 21 meters per second while 25 meters high. I have two questions. First question is, how high was the cliff? How high was the cliff? Okay. Well, let's think about it. So we have 2 points in time. So we can use GH1 plus 1/2 V1 squared equals GH2 plus 1/2 V2 squared. So the question really becomes, can I identify the multiple points? Can I figure out how everything is going to connect? Well, I know 1 point in time, all right? 1 point in time, it's moving 21 meters per second. I'll call it V1. It doesn't have to be the first time. It doesn't have to even be before. It just has to be 1 point in time, okay? And well, 25 meters high, 9.8 times 25. The only thing that matters is that the 25 and the 21 are paired together on the same side of the equation. It could be on the left side, it could be on the right side. It doesn't matter. So if I'm looking for how high the cliff was, I'm looking for some sort of height. 9.8, excuse me. 9.8 H2, all right? Now, do I have a velocity to pair with it? Oh, I do. The velocity that is going to pair is because it said from rest. So when it's at the highest point, its velocity is 0. Now, it's really easy. It is really easy. You just plug it in and you just solve. So 9.8 times 25 plus 1/2 times 21 squared. That's 465.5 equals 9.8 each. Divide both sides by 9.8. Divide by 9.8. So we have the cliff was 47.5 meters high. That's the height of the cliff. We could figure that out just by knowing one point in time its height and velocity. Because everything that we know from before is true. At the top, it's all PE. When it hits the bottom, it's going to be all KE. All right? That's it. That's how this is going to work. You just have to recognize and identify what pairs of information go together and plug them into the equation. That's it. So the points in time are what matter. You've got to be able to visualize the situation. Well, the biggest mistake that students do with this equation is they mix up the points in time. They'll take a velocity from one point in time and mix it with a height at another point in time. That doesn't work. If you really want, you can, you can check your work. Like, you can mathematically calculate it out. They need to mathematically equal. Every point in time has to mathematically equal the same number. So you can kind of just like double check your work in that way. So when we did this in the chart, each second was a point in time. So ironically, for people who are like, I had trouble calculating the heights, you can use this equation for the charts that we did on Monday. This still applies there. This always applies there. I don't want you to think that I'm just teaching you something that you only use it for this. I want you to have the expansive thinking and understanding that this is now another tool I have in my toolkit, and I can now use this whenever applicable. So you can use this on roller coaster problems. Like when you were filling out the H's and the V's, and you're like, oh, I have to solve for the PE, I have to solve for the KE, then I get the V, then I get the H. If you knew the H and V at one height, you could just go ahead and get the H's and V's at the others. So you have tools, use them. But there's one more thing I need to show you, something that's very important to me. Here's this equation. GH1 plus 1/2 V1 squared equals GH2 plus 1/2 V2 squared. I want to show you something. I want to show you something with this. What I'm going to do is I want to kind of get the V2 by itself. Why? Just hang tight with that. I want to get the V2 by itself, and you're going to see why in just a sec. But let's see if we can do this. All right, I'm going to do some algebra here. Well, how can I combine anything? Well, this is what I'm going to do. I know that I can do this. If I minus GH1 from one side, I have to minus GH1 from the other side, so that algebraically it could be true. So I'm left with 1/2 V1 squared equals GH2 minus GH1 plus 1/2 V2 squared. All right. I can't subtract GH2 minus GH1, but what I can do is I can factor out a G. All right, I'm just going to bring everything else down. Why did I want to factor out a G? Because I know that when I subtract the heights, when I subtract final height minus initial height, or H2 minus H1, that gives me the displacement. That's what we did on the charts. When you subtracted the heights, it gave you the displacement. So when I have h2 minus h1, that's really displacement. So I'm going to call that GD. D is displacement. So I'm just taking this in and replacing it with a displacement. All right, 1/2 v2 squared equals 1/2 v1 squared. Now gravity is just an acceleration, right? Gravity is an acceleration. That's all gravity is. So instead of calling it gravity, can I call it acceleration? A. Gravity is just acceleration, so let me just call it an acceleration. But gravity is a negative acceleration, right? So I need to make this a negative acceleration because gravity is always negative. All right, so now I know we didn't normally use signs with the energy, but let's just go ahead and see what happens. We know that gravity is negative. So if I'm going to have an acceleration, I'm going to say it's negative. So I don't want the negative. I want to get the v2 by itself. So what I'm going to do is I'm going to add AD to both sides. So I have 1/2 v1 squared plus AD equals 1/2 v2 squared. You know what, let's get rid of these halves. Let's just multiply everything in this by 2. So if I multiply everything by 2, both sides by 2, so this is going to become v1 squared plus, I got ahead of myself. Whoops, there it is. Sorry about that. I didn't multiply by 2 yet, so 2AD equals v2 squared. Huh. Now that's interesting. What if instead of calling v1 and v2, I called it v0 and v? What if hey, isn't this a kinematic equation? Isn't this the third kinematic equation, v squared equals v0 squared plus 2AD? That's where this equation comes from. This equation that we've been using all year comes from this derivation from the energy equations. I know, your mind is blown. It's actually really awesome if you think about it. In physics, when you take this in college, you will be able to put equations together to form new equations. This equation that we've been using all year is essentially the same thing as the equation that I just taught you today. The beginning and the end of this class are the same. Everything is connected. Did you know we could have used the energy equations for projectile motion, and we could have calculated the speed at any given point in time in the air just using the energy equations, and we wouldn't have had to worry about the angles and all that stuff? We could have. I think the angles are important, and you can actually do more with the angles than with the energy stuff. But everything is connected. I don't want you to compartmentalize your learning. Every time you learn something, and this might be the last time that I'm talking to some of you, but this is the takeaway message that you need to have, that every time you learn something, understand how it fits into what you already know, and understand how it can connect to other things. Do not compartmentalize. Do not put into individual silos your pieces of learning. Everything is connected. You need to understand how everything in the world connects with everything else and make meaning of it. Because if you can do that, you will have so many more skills than people who don't understand that you can use one tool for multiple purposes. So, I'm going to post today's assignment. It's going to be working with these equations, not too bad. Next week, we're going to have a quiz, and I'm going to have a video to talk more about that. But just so you know, I want you to understand that when you take the quiz next week, your Chromebook will be locked. So it might be a good idea if you're particularly bored. The quiz is on energy, all energy, 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 energy. So don't worry about stuff before energy, just the energy stuff. And again, I'm going to have another video to explain what's going to be on that. But it might be a good idea to go and take some notes and put equations onto one sheet of paper, maybe some definitions, some concepts, so that when your Chromebook is locked, you can just easily reference the things that you need to be successful on that assessment. That's coming next week, and I will see you guys then. Good luck.